Okay, ninth graders, today we're going to talk about Newton's third law. And of course, we've already talked about Newton's first law, which is known as the law of inertia, which states that objects will continue to do basically what they're already doing. An object at rest tends to stay at rest. An object in motion tends to stay in motion unless some other outside force acts on them. The second law is basically F equals ma. And again, the main ideas of that law are if you push harder on something, it will accelerate more. If something is more massive, it will not accelerate as much, assuming you push with the same amount of force. So now we're moving on to the third law. And again, this is something you've probably heard before. You might even be able to recite it. But it basically says that every action has an equal and opposite reaction. Now, what this really means is that all forces come in pairs. If I push on the wall will push back on me. If I sit on the chair and push down on the chair is going to push back on me. There are no singular forces in the universe. The earth pulls on the sun pulls on the earth exactly the same amount. And so we call these pairs action-reaction pairs. And I like to just put it into caveman speak. Caveman say, I push on rock, rock push on me. And you can do that for any pair of objects that are exerting forces on one another. Earth push on sun, sun push on earth. It really simplifies things. So here's just a short little video.
Newton's third law says simply when one body acts on another, then the second body acts back on the first with an equal and opposite force. So, simple example. I'm leaning on the desk. Why aren't I falling over? What's stopping me falling over? The desk. So, as I push on the desk is pushing on me. There's an equal and opposite force. I'm pushing on the desk is pushing on me, and it's stopping me fall over. Now, slightly variant on the same thing. I'm going to push on the desk. I push on the desk, and off I go. Why did I accelerate? Why did I accelerate? So the response or the acceleration comes from the Newton's third law pair. I'm pushing on the desk pushes on me, and that's why I moved away. Okay. Why did the balloon accelerate? There's a force involved. It accelerated, right? That means there's a force on the balloon. Where did the force come from? There's a Newton's third law thing going down here. Here's the balloon. It doesn't matter what's outside, it's full of air. But because of the pressure of the balloon, the elastic force of the air, the balloon pushes air out. That's one force in this process. There is a Newton's third law of force that acts in the other way. The air that's being expelled pushes on the balloon, which means the balloon accelerates. So it's the act of throwing stuff out the back, pushing stuff out, that causes the stuff that's pushed out, the Newton's third law, other force, pushes back on the balloon and accelerates it. What I've got here is a simple plastic bottle, but if you look on the outside, there's a couple of vents that are angled backwards. If you have a look closer, you can see the vents. I'm going to fill it with liquid nitrogen and boil it. So, liquid nitrogen. As I say, one of the neat things about being a physicist is you get to play with some really fun toys. This is liquid nitrogen, which is one of the more fun ones. It's about a couple of 100 degrees below zero. Now, you probably need the... So what I've got is I've got a boiling liquid. Hero did this with steam. I'm going to do it with liquid nitrogen, and I'm going to warm up the liquid nitrogen by putting in, this is just ordinary water. And we get this wonderful little jet engine. So what's happening? There's high pressure in here. The pressure forces, warm it up again. The pressure inside forces the gas out, and the Newton's third law reaction force pushes the cylinder in the opposite direction, causing it to spin. There's a force of this plastic bottle on the gas going out, and there's a Newton's law force of the gas on the bottle spinning it in the other direction. And I have a jet engine here. Now, this is not an ordinary fire extinguisher. Every single reduction valve has been removed from this thing, so it's a fairly lethal fire extinguisher. When I crack the valve, it will empty itself in about 10 seconds. And I'm going to sit on the skateboard, hold on to this thing, crack the valve, and hopefully I will hurtle along behind the building. There's a huge force of the cylinder on the gas. And then that gas pushes back on the cylinder and on me, accelerating me. So
4, 3, 2, 1. Hey, Dad.
What?
Why?
Okay, so one important thing to note about action-reaction pairs is that they do not cancel each other. These are not the same as balanced forces. They are similar in the sense that they are equal and they are in opposite directions. However, balanced forces occur on one object. Action-reaction forces act on two different objects. Each object exerts a force on the other, so they don't cancel each other out. So again, cavemen say, I push on rock, rock push on me. And just a reminder, balance forces cancel because they are on the same object. All right, here's another good little video.
There are a lot of misconceptions out there, and this is a video about one of the most common ones. So I went around asking people, what makes the moon go around the Earth? And they told me,
the Earth puts a gravitational force on the moon.
but does the moon put a gravitational pull on the Earth?
Pull on the Earth? Yes, it does. Hence we have tides, etc.
The moon pulls on the Earth too. It affects like the tides and women and stuff. It does. Very powerful, this thing.
Does the moon pull on the Earth? Probably that as well, yeah. So what I want to know is how does that force that the moon exerts on the Earth, how does that compare in terms of size to the force the Earth exerts on the moon?
Well, no scientist, but I think that one would be more powerful than that one.
It's got a greater force coming from the Earth because it's a greater mass.
Because the Earth probably has more mass.
Because it's a bigger mass. I thought greater mass is equals more force.
Does the moon pull on the Earth?
Yes, but a lot less.
Yeah, not as much as the Earth pulls on the moon.
Yeah, but a little bit.
Not very strongly.
Yes, but much, 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 much smaller.
Because of its mass,
less
its
mass.
size.
Because it's smaller. It's much smaller than the Earth. Because it's smaller. Because it's smaller?
Allow me to let you in on a little secret. Everyone got it wrong. The force that attracts the moon to the Earth is exactly the same size as the force that attracts the Earth to the moon. So what's going on here? Why did everyone get it wrong? Well, I think it comes down to cause and effect. The effect of the force on the moon is quite clear. The moon goes in circles around the Earth. But the effect of that force on the Earth is basically negligible. The Earth barely wobbles at all. So people interpret this negligible effect as indicating there's very little force affecting the Earth. But that is forgetting the third key piece of the puzzle, which is inertia. Inertia is the tendency of mass to maintain its state of motion. Since the Earth has a greater mass, it has a greater inertia. And so even with the same amount of force on it, it doesn't accelerate that much. Now, the funny thing is, many of the people I interviewed could state Newton's third law, which is every force has...
an equal and opposite reaction.
Something about Newton's law doesn't seem to fit into that. You're good at this.
Which Newton's law are we talking about?
The whole equal and opposite force thing. Yeah, that one.
So tell me what you're thinking now.
Well, one would think that if the Earth is putting a force on me, I would be putting an equal force upon it.
So why didn't they apply it to this problem? Well, I think they may have memorized the words, but not really believe Newton's third law in their core. Did they really feel it in their spleen? I don't think they did. So, allow me to try to convince you, all of you, spleen included, that Newton's third law really is true. Let's consider two objects. Initially, they have the same mass, 1 kilogram each. So obviously, the gravitational force of attraction must be the same on both of the objects. Now let's add a second kilogram to the first object. The force on the second object will now be twice as great because that 1 kilogram is attracted equally to each of the kilograms in the first object. But what is often forgotten is that new kilogram is also attracted to the second object, meaning that the total force on each object is still the same. They're attracted to each other with an equal and opposite force. We could add a third kilogram, and we would find the same thing. The force on both objects is still the same, even though the object on the left has 3 times the mass of the object on the right. So we can see that no matter what the mass, any two objects will have the same gravitational force towards each other. Can you feel Newton's third law in your spleen now? It should settle inside you and become a part of you.
Or think about the example of a skydiver who is falling to Earth. And it says, draw a free body diagram of the person and indicate what forces are present, what causes those forces, and which forces are balanced pairs, and which ones are action-reaction pairs. Okay, so let's take a look at this skydiver who's falling to the Earth. Here is the Earth. And here's the skydiver falling. Again, I'm not going to draw an actual skydiver. I'm just going to draw a dot because this is a free body diagram. So what are the forces that are acting on the skydiver? We have gravity. Gravity is always acting. So where does gravity come from? Gravity is the Earth pulling on the skydiver. So this is Earth pull on skydiver. Okay. Now the skydiver is falling. There is also in the real world a force upward on the skydiver. And now that is not a normal force because there are no surfaces contacting. This is air resistance. So this is, we'll just call it AR. And where does air resistance come from? It comes from the air molecules pushing on the skydiver. So I'll say air pushing on skydiver. All right, so are these the only two forces acting here? No. The skydiver is also pulling up on the Earth. And the skydiver is also pushing on air molecules. Each of them is getting, should make those bigger, skydiver pushing on air. All right, so we have 4 forces that are going on here. And so we have action-reaction pairs and balanced forces acting here. So what are the action-reaction pairs? The action-reaction pairs, remember, are when one object pushes on another force or pulls on another object, and that object pulls back. So basically, again, think like a caveman here. Let's take a look at this force. Earth pull on skydiver. Well, what is the opposite of Earth pull on skydiver? It is skydiver pull up on Earth. So these two forces are action reaction. All right. Now you might say, well, wait a minute, why not air resistance and the force of gravity? They're equal, they're opposite, but they're both acting on the same object. See, here, these two forces here's the Earth, here's the skydiver. They are different objects. They each pull on each other. But here, these two forces result from different things, and they are acting on the same object. These two forces are balanced forces. And what do? They, because they're balanced in this case, they are making it so the object will not accelerate anymore. This skydiver has reached terminal velocity. All right, these two forces, the action and reaction pair, will not cancel each other out. And then finally, we have skydiver pushing on air, air pushing on skydiver. These two forces are action reaction. Okay, so on the skydiver, we have air resistance, that's pushing up on the skydiver. We have gravity, that's pulling down on the skydiver. We have some other forces. There is the skydiver pushing on the air. Every air molecule receives some of that force. There is the skydiver pulling up on the Earth. So which of these forces are action-reaction pairs? We ask the caveman. If Earth pull on skydiver, then skydiver pull on Earth. If air push on skydiver, skydiver push on air. Now notice that there are two forces on the skydiver. You have both air resistance and gravity. Now notice that these two forces are acting on the skydiver, the same object. So these are what we would call balanced pairs. But the air resistance is coming from the air. The gravity is coming from the Earth. And they are acting on the skydiver. So both of them are acting on the same object. Those are balanced forces. Okay, this causes the skydiver to stop accelerating, but the skydiver is still going to move. And then some of you might say, well, wait a minute, how is the skydiver pulling on the Earth? I mean, a person is really small compared to the Earth. And we don't notice the Earth moving as things fall to the Earth. And the reason for that, again, is like what we saw in the video, the effect is so small because the Earth's mass is so big. Think of it this way. The force the Earth pulls with is the same as the force the skydiver pulls with. So Earth is pulling on the sky, the force the Earth exerts on the skydiver is this, and what the skydiver exerts on the Earth is this, or vice versa. I don't remember which one I did. Here we go. Yeah, so the skydiver is pulling on the Earth, which has a giant mass, and therefore it's going to have a tiny acceleration. The skydiver has a tiny mass compared to a huge acceleration, relatively. Again, the acceleration of the Earth is, on the order of 10 to the minus 23rd, maybe times 10 to the minus 22nd meters per second. Again, for all practical purposes, it's zero. The forces have to remain the same, but the things that make up the forces do not have to be the same. And this acceleration is the effect that we notice. Here we've got a large mass times a small acceleration equal to a small mass times a large acceleration. Here, if you have a parent and child, each of them standing on rollerblades, and they push, hand to hand against each other, they will both accelerate away from each other. Now that the mass difference isn't quite as big as it is between the Earth and a person, here it's a parent who's maybe, 2-3 times the mass of a child. And the last slide here, this actually is a Newton's first law question. When you are going in a car that stops suddenly or crashes, you keep going forward. Why? Keep going forward because you already were going forward. The brakes are stopping the car, not you. Your seatbelt is there to keep you from going forward.